About the divergence theorem. Um, the concern in this theory is in some kind of way to connect Green's theorem with, in Green's theorem it talks about how the line integral can be evaluated by a double integral by looking at those partial derivatives. So is it also possible to have um, a very similar consequence from Green's theorem to be able to use the divergence to calculate the same thing? Um, so, so what, so what Gauss was able to do with this particular notion is to be able to connect a double integral and equate that with a triple integral. Well, you would think that that's obvious because if you have a double integral looking for the volume, you can equate that with a triple integral for the volume as well. So that's the idea, and that's how Gauss was able to actually prove this particular consequence. So let's see what it says. On last time, we talked about a surface being oriented, and you want the orientation either to be upward or downward. So here, for the divergence theorem, the concern would be you want the orientation to be outward. That is, that capital N is positive. And with that, you want to be able to measure how much, if it's fluid that's flowing, how much of that fluid deviates from the particular source point here. So you can measure that by the divergence itself. And so that's what Gauss is trying to get at. And I want to show you something here that I think is very neat. Not this. This is just very basic in terms of the divergence. If it's negative, positive, or if it's zero, what does that mean? If we have positive divergence, then the point becomes a source point. That is, the fluid is flowing from the particular point. If the divergence is positive, if the divergence is negative, we have a sinkhole there. So the source point actually receives the fluid, and then you might not have any type activity at the source point. That is not a source nor a sink. That is, the divergence is equal to zero. But here's what I want to show you. And it's actually contained within the theorem itself. Where did I put the theorem? There it is. The theorem's up there, up top. I didn't realize that. Here's this double integral, and Gauss says that you can compute the double integral. Basically what he says is what Green concludes with looking at the line integral. Gauss says that you can compute the same thing using a triple integral. Now I'm going to ask you this. Here's what I think is the interesting thing about this. The big thing about the divergence theorem is this triple integral, that I can calculate this double integral by using this triple integral based on the divergence. My question is, what is that? Would you say it is? It's the flux. This is the flux integral. So Gauss said, look, I can find the flux by not computing the flux. He said, I can find the flux by computing the triple integral on the divergence. Now here's what's even more interesting than that. That Green's theorem, and here is now the divergence theorem, and then in a few minutes Stokes' theorem, which evaluates the line integral, is equated to a double integral, is equal to a triple integral. So the line integral and the flux and the volume, it's all the same. And the energy that's being produced from a fluid that's flowing from a source, the energy around that particular vector field, if it's conservative, you get some very neat things. So basically, all three of these theorems are equivalent. Wow, good stuff. Now, there's a course called Vector Analysis. And in that course, basically, you run back and do everything that you've done here in Calculus 3. The neat thing about that class, and if I had time, I would show you here, it just takes a couple of minutes, is that you prove and you show that Green's theorem is equal to the divergence theorem, that is equal to Stokes' theorem, that all three are equivalent. No, it's not. Athens State has it, UAH has it, but it's vector analysis. And, I've had students to, years ago when I did have time and I could kind of get into all of this, I showed the equivalence. I think it's in the book too, by the way. And so I had students to leave here to work on their bachelor's, say for example, at Athens State, and they said, hey man, we made an A in that class. It was the same thing that we dealt with in Calculus 3 in this course, the same exact thing. So that's pretty neat. So now what we're going to do today is compute the flux by looking at this triple integral of the divergence. Sometimes in the homework it may say compute both sides, look at the double integral, see what you get, look at the triple integral, see what you get. Well, for me, just look at this triple integral. I'm only satisfied with this guy right here, okay? So let's see. So use the divergence theorem to evaluate the outward flux of F through the surface of a solid bounded by the graphs of the equations, here by examining the divergence. So if I here compute the divergence of F, you remember it's the partial of M with respect to X plus the partial of N with respect to Y plus the partial of P with respect to Z. So it's a scalar. So here we get 2X plus 2Y plus 2Z. Now this solid is bounded here the solid region. X goes from 0 to A, Y goes from 0 to A, and Z goes from 0 to A. So we have this triple integral of the divergence, which we get 2x plus 2y plus 2z. And here, if we use dz, dy, dx, each one goes from 0 to a. So here we just evaluate the triple integral. So we integrate with respect to z first. Here the integral from 0 to a. We're going to put that 2 out in the front. We could do that, or you just leave it in there. Doesn't matter. 0 to a. So we get 2xz plus 2yz plus z squared, and z is evaluated from 0 to a. dy dx. So we get the integral from 0 to a, the integral from 0 to a, and this gives us 2ax plus 2ay plus a squared dy dx. Now integrate with respect to y. This is 2axy plus 2ay squared over 2 plus a squared y. And y goes from 0 to a. So we have the integral from 0 to a We're evaluating the y, so this is 2a squared x plus a to the third plus a to the third dx. So we can simplify that. This is the interval from 0 to a. Two a squared x plus 2a to the third dx. So then we integrate with respect to x. We get a squared x squared plus 2a to the third x. X is evaluated from 0 to a. So we get a to the fourth plus 2a to the fourth, and that gives us 3a to the fourth. Okay. Well, that problem is good. Let's see. Yes, sir. Just the bounds for its region, Q. All right. Do you have it? Let's see if you can work this one out. Give you a hint there. You want to convert those values for S to polar coordinates or cylindrical coordinates, if you will. Cylindrical because it's in the third space with the triple integral. Yes, sir.
What you do right here to get this? I mean, I see right here that you just went ahead and took the derivative, I guess, of this right
Yeah,
here.
it's called the divergence.
But
It's
did you?
it's the partial derivative of m with respect to x, which is just 2x for that problem. The partial derivative of this guy with respect to y, it should be x, y, z.
Oh, okay, that's it. Okay.
Yes, sir. That's what you were missing.
Yeah.
Yep.
I had to remember that.
Yes, sir. Mm-hmm. Did you get 0? Let's see. So you take the divergence of F, that's 2x minus 2x plus 2xyz, and that just gives you 2xyz, 2xyz. And then z is given by this radical, so we need that. If we convert to cylindrical coordinates, then we have x, y, z, but we'll use r, theta, and then z. So r goes from 0 to a. Here, for x and y, it's a complete loop. So theta goes from 0 to 2 pi. Then z goes from 0 to the square root of a squared minus r squared. And so we look at that triple integral. So here we have 2x, y, z with respect to the change in the volume over the solid. We use our coordinates here. So this is 2. The x is r cosine square, and then the y is r sine square, and then the z is the square root of a squared minus r squared. So we have 2. So there are 3 r's, so it's r to the cube, but then for cylindrical coordinates, you've got to have that r factor anyway, so it's going to be r to the 4th. R to the 4th cosine theta, sine theta, and then this is times a squared minus r squared. Now, here's what I do, and here is just my little hintful trick. Anytime I'm dealing with a complete loop, I always want to evaluate first based on the angle, because that may give me 0 first. And if I get 0 first in the integration, then I'm done. So what do I mean by a complete loop? Well, this is going from 0 to 2 pi. Right? So I'm going to put d theta first. So this is d theta. Doesn't matter about over here. Hopefully everything cancels out at theta. If not, then you got the rest of that stuff to work anyway. Okay, r should be last. So theta goes from 0 to 2 pi. Z goes from 0 to the square root of a squared minus r squared. And then theta goes from 0 to a. Now when you integrate with respect to theta, we let u equal to sine theta. Du picks up cosine theta. So we have the integral from 0 to a, the integral from 0 to the square root of a squared minus r squared, and this is 2r to the 4th sine square theta over 2. Here evaluate the theta from 0 to 2 pi times that radical a squared minus r squared dz dr. What is sine of 2 pi? What is sine of 0? So this whole thing is 0. You're done. Is that what you did, Joshua? No. What did you do? No, you can't do that. just because you know the answer is 0, so you don't go hunting for 0 in the beginning. You let 0 work itself out, man. It's just like me putting the answers on the test, and then you just do some scribble scratch and put the answer down there and say, "Hey, I got 6." You the answer is 6, right? Okay. Well, how'd you get it? I don't know. I just scribble. Yeah. And I've seen some stuff like that. I'm like, no, you need to show me. Well, that way, yeah, yeah, man. Your way, man. You cut some really important corners. See, if z was static like that, where z is fixed to be 0, then you're done. But see, z goes from 0 to the square root of a squared minus x squared minus y squared. Hmm. Yeah, you can reduce z if just the xy plane. But then, in particular, you want to be concerned about what happens to the angle. Now, I could have changed that and restricted theta from 0 to power over 4, and you would not get 0 for your answer. Just because if z is 0, that has no bearing on x and y. You still want to investigate what's happening in that surface region with x and y. Now, let's look at this one. Now, I like this one because if you look at this surface is a sphere. It's a sphere with radius 3. So if I know that, then we can make here the work a little bit easier to solve. Let's first compute the divergence of F. So we get 1 plus 1 plus 1. We get 3. So here, this triple integral over the solid is that divergence, which we got 3 times the change in the volume. Well, the volume here is fixed based on this surface region. So this becomes 3 times the volume of the sphere. This is 3 times, what is that, 4/3 times pi r cubed? Well, here, r is equal to 3. Here the radius. So this is 4 times pi times 3 to the third. So it gives us 27 times 4, which is 108 times pi. Now, what helps us with that? Here's the thing about what helps us, that I can go directly to that algebraic formula, is because the divergence came out just to be a number by itself, 3. There's no x, y, and z involved in that divergence. So I can just use that 3 then times, this says the volume, right? So 3 times the volume. I'm done. All right, let's see. Let's see what you can do with that one. And again, if you look at the loop for x and y, it looks like r goes from 0 to 5. Theta goes from 0 to 2 pi. And then z tells us directly it goes from 0 to 7. So in that triple integral, if I were you, I integrate first with theta. see what happens to that loop. Okay, you did it the legal way. That's right. That's right. That's what that was the joke they said about Doc Holliday that when it's still questionable how he got one of Wyatt Earp's badges, and they said that he allegedly gunned down Ringo in a gunfight, and the tale was that since Doc Holliday had a badge, that he did it the legal way. So, but everybody knew Doc Holliday was a killer. So, hmm? I read the book. Yeah. The book is fascinating. It's the book that I read pulls excerpts from Wyatt Earp's autobiography, which the movie Tombstone is based on that. The Yeah, the movie Tombstone, then I think the movie Wyatt Earp. Matter of fact, that stuff is so fascinating. I didn't know this, but when you read this stuff, you kind of figure out a whole lot. All of the Western heroes that you've ever seen, Matt Dillon, all those guys, the sheriff, the marshal, whatever, he's straightened up the town and that type of thing, whether it's Clint Eastwood or Gary Cooper, they're all based on one character. It was Wyatt Earp, every last one of them. Every last one of them. Yes, sir. Yes, sir. The original writers for the Western genre, they only had one character to go on that they kind of trusted because they had a book based on him. And he would hang around, the set when he was an old guy in his 70s. And Wyatt Earp would come and check things out, and they would kind of ask him questions and that type thing. So, yeah, man, yeah, Earp was the real deal. I kind of like him because a lot of folk don't know this side about him. He was a churchman. I want to say, I think they made him a deacon in his church. He didn't drink, he didn't smoke, I mean, he was a clean, yeah. But he kind of cracked when they killed his brother. But I'd probably do the same thing. Yeah, man, So the law didn't really help out, and so he kind of took things in his own hands. Back in those days, you could probably do that. Anyway, let's get back to this stuff, man. So Joshua said he did it legal. Good. The legal way. Well, that's all right. So here, the triple integral, and you got that divergence to be 2y, this is dv with respect to the solid, and so that comes out to be here this triple integral 2r squared. I'm not going to work it out because once you see this, I think you get it. D theta, let's see here, dz, and then dr. Theta goes from 0 to 2 pi, z goes from 0 to 7, and r goes from 0 to 5. And when you integrate with respect to that sign, you get cosine. You're evaluating cosine from 0 to 2 pi. You get 0 there for that loop. So this is 0. Good. One more to do. I'm going to let you do this one. See if you can get that answer over there. But don't have the answer kind of thinking that I'm trying to get that answer and, I don't get it. Just work it out. And if you work it out, and I'm going to see if you don't run into a mistake from calculus 1, calculus 2. If you can avoid that mistake, you can work this problem and get the answer. The divergence is just 3e to the z, right, for that divergence. You have your bounds there for s. This is e to the z plus e to the z plus e to the z, 3 times e to the z. And then s is bounded here. X goes from 0 to 6. See that y goes from 0 to 4, and z goes from 0 to 4 minus y. I think I was saying q, but this is actually the region for s. got it? Okay. Everybody's happy? Joshua said no. Let me tell you, if there is a mistake, there's probably a mistake in the evaluation at 0, that lower bound, because you got some values in there that just doesn't necessarily go out to be completely 0. Let me show you. So we have this triple integral, and that was 3 times e to the z. Let's say here we use dz first, dy dx. Z goes from 0 to 4 minus y. Y goes from 0 to 4, and then x goes from 0 to 6. So we integrate first with respect to the z, and this gives us, put that 3 out in front, 0 to 6. Next integral 0 to 4. Integrate e to the z, you just get e to the z. So this is e to the z evaluated from 0 to 4 minus y, dy dx. So this is 3 times the integral from 0 to 6. This is the integral from 0 to 4. We evaluate, this is e to the 4 minus y minus e to the 0, which is 1. So this is 3 times the integral from 0 to 6. This is the integral from 0 to 4. This is e to the 4 minus y minus 1 dy dx. Integrate now with respect to y. When you integrate e to the 4 minus y, you have to use a u du substitution, so that u equal to 4 minus y. Du is negative dy, so you have a negative there. So this is 3 times the integral from 0 to 6. This is negative e to the 4 minus y minus y. Y is evaluated from 0 to 4 dx. This is a 3 there. So this is 3, the integral from 0 to 6. You have negative e to the 4 minus 4. No, sir. Just a 3. Just a 3. I'll put the negative here. So then this is minus 4, and then we evaluate at 0, so this becomes plus e to the 4 plus 0 dx. Since there's no x there, that's just 6 times all that, so you get the 18. This is negative e to the 0 minus 4 plus e to the 4. Right? E to the 0 is 1, that's negative, so this is 18 times e to the 4th minus 5. Again, when you have that e to that power, you start evaluating at 0. Just because you got a 0 down below doesn't mean that that whole term is equal to 0. E to the 0 is 1, so you got to watch out for that. Any questions? All right. Let's take a 5-minute break, and we'll come back and look at the last section.